Okay, well, now we will move to the synchronizing power coefficients. Okay, um, synchronizing coefficients, they are a family including the torque, the synchronizing torque coefficients. Okay, I will not discuss synchronizing torque coefficients here. Okay, if you want to know more about the synchronizing torque coefficients or more details about also these synchronizing power coefficients, please register in my classes of the advanced power system or also in the course of power system dynamics. Okay, here is just a very brief introduction. You can find something similar in Condor book or also in Stevenson book. Okay. What is the idea of the synchronizing coefficients? Synchronizing coefficients, they are used to describe some system properties that they have a strong influence on the dynamic behavior. Okay, as you must remember, if we are operating the power system, the first concern is security. Okay, security is the most important aspect when you are operating power system, probably the first one, because you need to keep the lights on. I mean, security is keeping the lights on. And then when you keep the lights on, then people from power system economic, they can jump in and they can run optimal power flow and optimal dispatch and so on, and they can minimize the cost of the electricity and produce electric electricity as cheap as they can for the customer. Okay, but the first concern is security. Security means, for instance, in this case, keeping the system safe, keeping the lights on, and of course, the system must be stable. The system must be stable. The machines, the synchronous machine must be synchronized, and that is the first concern. And that is happening in all time scales, especially if we are working in a steady state, if we are providing electricity to the loads, even for very small, very tiny temporary power change, the power system must stay stable. That means that the generators must stay in synchronism. Okay. What I will do now is use a very simple analysis to describe and to define the synchronizing power coefficients. Okay, let's say that we have a synchronous machine. This synchronous machine is connected to the system, and I will do a very small changes from the operation condition. Okay, as you can see over here, for the electrical power, I concern about the angle and the electrical power, yes, because they are related through the power angle equation. Okay, imagine that we are working in a steady state. The initial angle is delta zero, and we are delivering a electrical power that is PLX0. Okay, and then we increase a bit, very small changes on the angle that they create changes on the active power or other way. Okay, what I'm saying is, let's create a displacement, a very small change, incremental change. We use delta to describe those incremental change. In this case, a small incremental change on the angle delta and a small increment change on the electric power. Okay. You must remember here we have the equation that this is the power angle equation. Over there, the coefficient P max is constant and delta is the internal angle of the machine and electrical power, the power delivered. Okay. When we include these small changes, what I am doing is putting inside the equation the small changes. And what we get over there is a very interesting equation. Okay. On the left-hand side, there is no major concern. It's a linear relationship. On the right-hand side, I have a major concern because it's a sign, and that is the sign of a sum. Okay. You must remember that that sum can be using trigonometric functions. We can try to expand that. The sine of the sum is equal to a sine multiplied by a cosine plus a cosine multiplied by a sine. Okay, you must remember that from Mathematics 101. Okay. And what I want to do is the following. If the incremental displacement is very small, if the incremental displacement is very small, we can make two assumptions. First, the cosine of that is almost 1, yeah, because the displacement is very small. And the other thing is that the sine of the delta displacement, the delta capital, delta lower letter, it's equal to delta delta. Okay? Making those assumptions, we can obtain something quite interesting. Look over here, the equation. We have a very interesting equation because here we have a sine of delta zero, and that is already PLX. Okay? And on the other hand, we have delta delta multiplying a P max cosine of delta zero. What I'm trying to say is something very interesting. What I'm trying to say is that we can transform the small incremental displacement and refer the power angle equation in order to include what is the changes delta delta on the electrical power. Okay, what I am saying is here I include, let me tell you, here we include the displacement. Yeah, we put here the small displacement, then we use those properties over here, we simplify, and then here is the important consequence. Okay, because here this is the accelerating power. P accelerating is equal to P mechanical power minus electrical power, but that is coming from this equation over here and is inside. And the important conclusion is that at the end, when we have a displacement on delta, that represent a change on the accelerating power that can be described by P max, the cosine of the initial angle, plus the changes on the displacement. And that is quite important because from there, I will put this, the accelerating power, into the swing equation. And when I put that into the swing equation, remember, this is coming from the previous slide. This is the accelerating power, and the accelerating power is equal to this. Okay? Well, what I want that you understand is this new equation over here. That is a version of the swing equation to include the changes caused by this small deviation. Okay? And what is interesting is that if we now take how the electrical power change, if we calculate how the electrical power change in terms of change of the angle, if we do so, we will realize something quite interesting. What we will realize is that the changes on electrical power versus changes on electrical angle, they are constant, and they depend on the Pmax that is already defined and the cosine of the initial angle. Okay, this term that I present over here is what we call the synchronizing coefficient. And what is the synchronizing coefficient? Well, the IC 60050 define the synchronizing coefficient like the quotient of the change in electrical power by a variation on the rotor angle displacement. This number is extremely important because it's saying if the rotor angle change, the electrical power change, and that proportion, the inverse of that proportion is represented by the synchronizing coefficient. That is what you need to understand here, okay? And more important, I can use this synchronizing coefficient here, and then I will obtain this equation over there, okay? What is the important part? The important part is that small angle deviations create small changes on the electrical power. That small change in electrical power is translated into acceleration power. The thing is that the accelerating power depend on the size of this small disturbance, and that is related by using the synchronizing coefficient. But the beauty here is that if you look this new equation that we have over here, this is a second order differential equation, okay, in terms of delta delta. Here we have a constant, okay, a constant. But the synchronizing coefficient is who is defining the shape of the solution of this differential equation. What I'm trying to say is the solution of the differential equation will be the changes on the rotor angle. And how those changes will be depend on the synchronizing coefficient. Now, what we need to examine, let me go to the next slide. What we need to examine is if this synchronizing coefficient is positive. If this synchronizing coefficient is positive, that means that the exponent that will appear at the response will be negative, and as consequence, we will have oscillations, and those oscillations will be dampened. But what is the worst case scenario? If the synchronizing torque is negative, wow, now we have problem because the solution will increase size over the time, and we will have this kind of behavior that is an oscillatory and exponentially increasing, okay? In this case is exponential increase. In this case it will be, this is the change in delta, okay? And we will have something like this, okay? And this is over the time, okay? Good. Good. One thing, small signal stability can be described by the synchronizing coefficient. Synchronizing coefficient positive, we want that. Negative, we don't want that because that will create problems of instability, okay? But what's happened if we have a positive, a very positive synchronizing coefficient? Okay, that the oscillation will be a simple harmonic motion, and that motion will be defined basically by a frequency that can be obtained by this equation over here, okay? Okay, I believe that you need to understand two things here. The conclusion of this section. One, the synchronizing coefficients allow you to understand how the electrical power change when there is small variations on the power angle, okay? Be careful, I am using the word small variations. Second, if the synchronizing coefficient is positive, that is what I want because the system will be stable And there are some oscillations, but those oscillations are simple harmonic motion, okay? And we can use that equation over here to define the oscillation of that, the oscillation that we will get on delta, okay? But if the synchronizing coefficient is negative, no, that is a very bad problem because the system will be non-oscillatory unstable, okay? Okay, now I must start to talk about probably one of the most beautiful things that we can use for assessing transient angle stability, okay? I will start talking about the equal area criterion of power system stability, okay? Before I start, you must remember that I introduced the concept of infinity bus bar, okay? The following discussion from here onwards, I will assume that the synchronous generator is connected to an infinity bus bar, okay? In this case, the infinity bus bar, you must remember, is a system that have a big inertia, okay? Have a big inertia, and as a consequence, this voltage is located and is constant magnitude and also constant angle. Typically, we assume that that voltage is a reference, okay? That is a typical assumption. 0 degree, okay, it could be 0 degree, it could be any angle, but it will be constant, and we will assume that the infinity bus bar is the reference, okay? And then what I will say is, okay, this machine is delivering power to the grid, and this reactance over here is the reactance defining the electrical interaction between the generator and the infinity bus in terms of active power, okay? What I was explaining is, if you want, we can create here the reactance network, and you can see here the reactance network. In this case here we have the model for the synchronous generator. We are using the transient model, that is a constant voltage source behind the transient reactance, okay? And then you must remember that for the electric power interaction, we need to take in account the total reactance that is connecting the infinity bus bar and the internal point of the generator, okay? What I'm telling you is that this reactance over here, is what is defining the electrical power interaction between the generator and the infinity bus bar, okay? Taking that in account, we can simplify the problem. By saying, well, for any power system, at the end, I can go and define a simplified model that is internal voltage connected to a infinity bus bar using equivalent reactance, okay? And now I would like to stop here and make an explanation. The power system can be as complicated as you wish. At the end, what you need to identify is the reactance that is interconnecting the source, that is the internal voltage of the generator, and the infinities bus bar, okay? If you have many bus bars, transformers, transformers, transmission line, whatever the topology is, you can use circuit analysis, or you can use admittance matrix, and you can get that reactance, okay? For that reason, it's not my job here telling you how to arrive over there, because my students are top experts on matrix calculations on power systems, okay? What I need that you understand, and that is my job here is explaining to you that the electromechanical dynamic of that system can be represented by the swing equation, okay? And in this case, the swing equation, you must understand something quite interesting. Here is the voltage of the infinity bus bar, and here is the voltage, the internal voltage of your synchronous generator, okay? And the angle between them, this is 0 degree, this is delta, okay? What I'm trying to say is when we are using the single machine infinity bus system, we translate the whole system into this small one, but the electromechanical dynamics is defined basically on the angle delta, and that angle delta is the relationship or the phase angle between the infinity bus bar, that is the reference, and the internal voltage, okay? Good. And the other thing that you must understand is that the electrical power is defined by this equation, where again, it's not my problem, but you will be able to use any method to obtain the reactance that is defining the electric power interaction between the generator and the infinity bus bar, okay? Okay, over there we have the two important equations, and the first thing that we need to do is let's think about equilibrium points. And for the equilibrium points, you must remember from mathematics, we define equilibrium points where the derivative term is zero. And in this case, if we make this point zero, that means that when this condition happen, electrical and mechanical powers are equal, we are in one equilibrium point, okay? Sorry. If we extract from this equation delta, we can obtain here the equation for delta, okay? The interesting thing is if we have a mechanical power and we intercept with the plot of the electrical power, there are two intersection points. One intersection point here before 90 degrees, this is in radian, but this is 90 degree, and this one is, sorry, and this one is 180, okay? Okay, there is a intersection here before 90 degree, and there is another after 90 degree and 180, okay? And we can obtain those values. Yes, we can do it very simple, and we can obtain, for instance, this one here, okay? What I'm telling you is the following. What I'm telling you is that there are two equilibrium points. One equilibrium point that is below 90 degree, and that is this one, and one that is after 90 degrees. The one that is after 90 degree, and that is what is defining the maximum, okay? And then we have another one that is delta max, and that is the second equilibrium point, okay? However, I need to make a comment about those equilibrium points. This is a steady state point. The machine can work here, and this is a stable equilibrium point, okay? But this one here is again an equilibrium point, but this one is unstable equilibrium point. What is the reason that is an unstable equilibrium point? Well, it's very simple. If you notice over here, when you move in this way, delta increase, and when you are moving in this way, the electrical power is increasing. What I'm trying to say is here, dp, the delta is positive. And that is what we want. We want that the machine is able that they will give you more power when the power angle increase. However, after you pass 90 degree, you start to go down the hill because here dp, the delta is below zero, and increases on the angle means decreasing on the active power. And we don't want that because it's not helping to uh, stabilize the system. In that case, you are reducing the active power, when the active power is more needed. And that is the reason that that equilibrium point is unstable, okay? Well, from this slide, I need that you understand the following. The blue line defines the electrical power. The blue line defines here the electrical power, okay? The horizontal lines that we plot here, represent mechanical power. This is one, this is another, this is another, this is another. Each one of those lines represent mechanical power equal constant, okay? But what you need to understand clearly is that the operating points are defined by the intersection of mechanical power and electrical power, because the operating point will be mechanical power equal to electrical power, and that represents possible operating state, okay? Possible operating states. We define those points as equilibrium. And there are some equilibrium points that they are stable equilibrium points. I want the system working there. And there are some unstable equilibrium points that I don't want the system going there. Okay? Okay.